In lecture, we're going to discuss some of the effects that are going to be associated with hydrogen bonding. Now, one such effect is that the melting and boiling points of hydrogen bonded molecules or molecules where the dominant intermolecular force is hydrogen bonding. So for those molecules, the melting and boiling points are significantly higher compared to similar molecules which do not exhibit hydrogen bonding as the intermolecular force. So I've drawn this chart where the boiling points of different molecules are plotted. For example, in this green line over here, you're going to see the boiling points of H2O, of H2S, H2SE, and H2TE. They are in the same. They're in the same group, T, Se, S, and O. So their bonding is pretty much the same, but only H2O has hydrogen bonding as the dominant intermolecular force. So its boiling point is much higher compared to the rest of the molecules. The same goes for if you look at the diagram for this. If you follow this blue line over here, you're going to notice that HF, which has hydrogen bonding as the dominant intermolecular force, has a much higher boiling point compared to the rest of the molecules in the same group, HCl, HBr, HI. And the same applies to ammonia as well. And H3 has a much stronger intermolecular force. It has hydrogen bonding in it, but it's much stronger compared to the rest of the molecules which are similar to it. So it also has a higher boiling point, but although the trend is not exactly as dominant as can be seen in H2O, because NH3 is not forming a lot of hydrogen bonds. But what you're going to notice is that molecules exhibiting hydrogen bonds, they generally tend to have higher boiling points. One extremely important fact that we're going to discuss about hydrogen bonding is that water, whenever it freezes, it expands. So it expands when it freezes, and this has a lot of effect everywhere. You're going to notice if you freeze a bottle of water, and here is an image of a frozen bottle of water. This is normal water, and it's filled to this mark. But when you freeze it, that ice, when water turns into ice, it expands, and you would notice a lot more ice is formed. So whenever water freezes, that water generally expands, and the ice formed is less dense because the volume of the ice increases, and the molecules of ice occupy a much larger area compared to liquid water molecules. So we will try to explain this fact. Why do water molecules start expanding? Why do they expand? What happens to the structure of ice or water molecules? What happens to the arrangement of the water molecules as the temperature decreases, as the temperature drops and they start freezing? And why do they start expanding? And why do you notice a lot of ice overflowing or coming out of the bottle? This leads to a lot of cracked pipes in winters as well. So that it causes a lot of havoc in a lot of places wherever temperature drops below 0 degrees centigrade, below the freezing point of water. I've drawn a typical molecule of a water where an oxygen is bonded to two hydrogen atoms, and these hydrogens have a partial positive charge. So both of these hydrogens have a partial positive charge because they are bonded to an extremely electronegative oxygen which is pulling the electrons towards it. So this oxygen, on the other hand, has a slight or partial negative charge. And one of the reasons why this partial negative charge is very strong is because oxygen has two lone pairs. So those lone pairs have a very high charge density, and the strength of the negative charge increases. So this is your water molecule having a very strong partial positive charge and a very strong partial negative charge. Now in normal liquid water, the molecules of water, these water molecules, they are all really very energetic. They have a lot of kinetic energy, and they can easily overcome these strong hydrogen bonds. So they can arrange themselves in whatever manner they find convenient because the hydrogen bonding is relatively not strong. The molecules have a lot of kinetic energy. So here I have drawn the diagram. So all these water molecules, they have plenty of kinetic energy. They're in liquid state. They're all roaming around, buzzing around very fast, very quickly. They're all sliding past each other. So all these molecules, these arrows show the direction in which these molecules might be moving in a haphazard, random manner, all moving around easily. The hydrogen bonding, the attraction between the positive and the negative slight negative, partial negative, it would be attracting the partial positive, but relatively that attraction would not be very strong. The molecules have sufficient kinetic energy that they can overcome those attractions. So I've shown these attractive forces, these hydrogen bonds, using these dotted blue lines. The partial negative of this oxygen would be attracting the partial positive, but this molecule has sufficient kinetic energy, so it would be able to overcome the attractive forces and would be able to move freely. So all these molecules, they're all moving freely in random directions, and they can all rearrange themselves or arrange in whatever manner they like. Now what happens when these water molecules, they start losing kinetic energy? So all your water molecules, eventually when you start freezing them, they start losing their kinetic energies, and the molecules would start rearranging themselves according to the attractive forces. Relatively, these attractive forces would become stronger. Before that, the molecules had sufficient kinetic energy, they were able to move freely, but as they start losing the kinetic energy and they start freezing, what happens is that the water molecules, they start to rearrange themselves. So as an example, what would happen is that as this molecule loses its energy, the attractive forces become stronger and the molecule rearranges itself according to the hydrogen bonds, according to the attractive forces of the hydrogen bonds. So for example, the partial positive of this hydrogen would be attracted to the partial negative of this other water molecule. Similarly, this other water molecule would also slightly it would start rearranging itself. Its partial negative would be attracted to the partial positive of the first hydrogen. So this hydrogen partial positive would pull this oxygen and would try and attract it. So relatively, the attractive forces are now becoming more stronger. The molecules have lesser kinetic energy, so they can't just roam around freely now. Similarly, this water molecule over here, its oxygen would get pulled by the partial positive of this other hydrogen, and it would start getting attracted to, so they would start attracting each other, and the molecule would rearrange itself according to the hydrogen attractive forces created by the hydrogen bonds. So this partial positive would attract the partial negative of this oxygen over here. Similarly, if I pick this water molecule, this would also rearrange itself and it would be attracted to the partial positive. The oxygen of this water molecule will be attracted by the partial positive hydrogen. So as it loses its kinetic energy, this water molecule would also rearrange itself according to the attractive forces created by the hydrogen bonds. Finally, I have this last water molecule. It would also, as it loses its kinetic energy, it would also come and get attracted to the partial positive hydrogen of this other water molecule, and they would start attracting each other. Now, as you notice, what would happen as the water molecules, they start losing kinetic energy, they start to rearrange themselves according to the attractive forces created by the hydrogen bonds. The partial positive hydrogen would be attracting the partial negative oxygen of the other water molecule. The partial positive of this hydrogen would be attracting the partial negative of this other water molecule. So the molecules start rearranging themselves, and what this leads to is it creates a lot of gaps in between. And these gaps, it is because of these gaps that ice would start to expand. So initially, when the water molecules had kinetic energy, they were able to overcome the attractive forces and they were able to move around freely in whichever direction they wanted. So they were more compactly arranged. But when they started freezing, the attractive forces of the hydrogen bonds, they became more dominant, and they started rearranging the water molecules, and a crystalline structure would be formed, and the position of the water molecules would be determined by these hydrogen bonds that are forming between the partial positive hydrogen and the partial negative oxygen. So the entire structure of water would expand. There would be lots of gaps created between the water molecules, and this is the reason why ice expands. While liquid water is more compactly arranged, the molecules can freely move around in all directions, they have sufficient kinetic energy. But when those same water molecules freeze, a lot of gaps are created, and this leads to the expansion. This is the expansion that you notice when ice is formed.